When we want to know how many things we have, we simply look and count. But what happens when the total is completely hidden from view and all you can see are the pieces left behind? It is possible to identify the exact size of an unknown collection using nothing but the leftovers. Take a look at the parameters of Jane's egg puzzle. We have a basket of eggs. Counted by 3s, there is 1 egg left over. By 5s, also 1 left over. By 7s, there are 4 left over. And one final requirement: the basket holds fewer than 50 eggs total. Standard long division often treats a remainder as an awkward fraction, the messy excess that failed to fit into neat groups. In this system, leftovers serve as coordinates, pinpointing the missing whole with absolute precision. Counting by 3s with 1 leftover creates a pattern on a number line: 1, 4, 7, 10, and so on. The second rule, 5s with 1 leftover, generates a separate sequence. Stacking them reveals the numbers satisfying both conditions at once: 1, 16, 31, and 46. We have narrowed the possibilities down to 4 options under our 50 egg limit. Testing which of these leaves a remainder of 4 when divided by 7. 16 leaves 2. 31 leaves 3. But 46 divided by 7 leaves exactly 4. Layering these independent arithmetic constraints creates a logical funnel, filtering out the wrong answers until only the correct total remains. This method of filtering dates back to ancient Chinese mathematics. An ancient problem asks for a number leaving remainder 2 when grouped by 3s, 3 when grouped by 5s, and 2 when grouped by 7s. Building a grid for these 3 new patterns show they perfectly overlap at the number 23. However, if we remove the artificial size limit, 23 is only the first valid answer. This introduces the core mechanism of the Chinese Remainder Theorem, modulo arithmetic. In this system, numbers function as repeating cycles that wrap back to the start after reaching a set value. Because our group sizes, 3, 5, and 7, are relatively prime, their cycles synchronize predictably. Multiplying them reveals a period of 105. Counting forward by this period from 23 generates infinite valid solutions: 128, 233, and beyond. These intersecting cycles create a predictable rhythm that, when you count past 12 o'clock, the system resets. 13 o'clock is simply 1 o'clock in a modulo 12 system. Calendars use these same frequencies, layering the 7-day week over the rotating months to keep our schedules in sync. This logic underpins digital data encryption. When we scale these cycles, from small numbers like 7 up to prime numbers with hundreds of digits, the patterns become nearly impossible to reverse. Security protocols hide information within these massive numerical cycles. Finding the original data requires knowing the specific divisors used to create the remainder, a task that would take conventional computers centuries to solve by brute force. Finding order in these partial patterns reveals a universal structure hidden within the numbers themselves.